Hello and welcome back. This is problem J, Sushi from Atcoder Educational DP Contest. The problem states that there are n dishes numbered 1 to n. Initially, each I from 1 to n. The ith dish has ai number of pieces of sushi on it. So I, A1, A2, A3 up to n will be the counts of sushis on the ith plate. Sushi count on ith plate. Now, Taro will perform the following operation repeatedly until all the pieces of sushi are eaten. He will roll a die that shows number from 1 to n with equal probabilities and let I be the outcome from that rolling of dice, and he will eat one of the sushis that is present on the ith plate. So suppose I turns out to be 3, and if A3 is greater than 0, he will eat one of it so that it becomes A3 minus 1. Or if A3 is 0, in that case it remains 0. This is the operation that he will perform, and we need to find the expected number of times the operation is performed before all the pieces of sushi are eaten. So this is what we need to compute: expected value of the operations until which all the sushi on the table are eaten. That means ai becomes 0 for all I from 0 to n. For all I from 1 to n, ai becomes 0. This is the terminating case. The constraint for this problem n is up to 300, and the number of sushi on any plate I is 1, 2, or 3. So let's try to first understand what expected value is. The mathematical representation for expected value is given by this formula. Expected value for any event x is given as, so in our case the event was that the operations are performed and we need to count the number of times of operation count until the event terminates. So this event could be as simple as rolling a dice, and the value that we want to find out is what is the expected value of, let's say, expected value on the face of the dice whenever it is rolled. So this could be the value that we want to compute. In that case, this variable x event can take, let's say the dice has values from 1 to 6, then this variable can take values 1, 2, 3, 4, 5 and 6. This is the variable, so it can take the values. So this x belongs to this range, integral values in that range, and p of x denotes that what is the probability of x being that particular value that we want to find out, whatever we want for each value from 1 to 6. So if the event is uniform, in that case we may assume that each phase is equally likely to occur. In that case, the probabilities for the variable would be 1 by 6 for all. And following this formula, we will have the expected value of the face of the dice as sigma from x will take values from 1 to 6. The probability, the value times the probability that it is x in that event, which turns out to be the formula 1 times 1 by 6 plus 2 times 1 by 6, 3 times 1 by 6, and so on until 6 times 1 by 6. And after evaluating this, you will find out the expected value of this particular event. This is the main idea or formula for finding out the expected value of any variable. The variable in this case was the face of the dice. It could have been, let's say, 2 dice are rolled. So dice 1 is A, dice 2 is B, and we need to find out what is the expected value of x plus y. This could be another event. In this case, we saw that the event was x, and we only had 1 dice to consider, and we need to find out the expected value that will occur on the face of this dice. But another question could be that we need to find the expected value of sum of the values on the faces of dice. So in that case, this will be the event for which we need to find out the expected value. Now in this case, the expected value formula will be as follows. So x plus y can take values from 2 to 12, because the least value that x can take is 1, the least value that y can take is 1, and 1 plus 1 will be 2, and the maximum value that they both can take is 6, hence the sum can be up to 12. And the probability for finding out for each of them can be computed using this formula. So this is the idea for another question, which was finding out the sum of the values on the faces of dice on a uniform random experiment. That's it about this. So let's try to understand our problem in terms of what we have understood so far. So as we saw here, this had a terminating experiment. This was a terminating experiment, right? So let me explain you what it means by that. So we were determined that it was determined that the event occurs exactly 1 or 2 times, right? In the first example, we saw that we were rolling the dice only once. In the second one, we were rolling the dice 2 times. But in our case, let's try to take an example. We had the sushis as follows. Let's say 1, 2, 3, 0, 0, 1, 2. As such, the counts of sushis. Now we are randomly rolling a dice which has which can take any integer between 1 and n. So this can take any value. Suppose we end up at this index. The dice rolled up this index. In that case, this does not change the array at all, right? So it will remain same because we are ignoring, or we are not taking any sushi from this. No movement is possible. But if it arrived at a index where it is a positive value, where a positive value is present, in that case we will subtract 1 from that particular index, right? This will result in this array. So as you saw, this did not change, this changed, this became a dash, but this transition did not change at all. This kept the state of the array same as which was earlier in the previous state after making the choice. So this is the main constraint of this problem. We are given a non-terminating experiment. So this is a non-terminating experiment. And for this type of experiment, we need to find out the recurrence relation. Obviously, it is a converging because the probability of ending up at these indices is small and it will converge. So we will need to find out the equation or the expected value of the number of times this operation will be performed. Now let's try to figure that out. Before that, let me also give you the basic idea. So we will not store this entire array as a state. So if we had to store the values 1 2 3 0 1 2 1 as a state of the dishes, then it would be very difficult to subtract 1 from any particular index, then again arrive at some other state, because only one value is changed after performing a transition. Instead of that, we can store it in a similar format. We will store the counts of 1s, 2s and 3s. So our state would be C1, C2 and C3, where C of I denotes count of I in A. So this is same as storing only 3 variables, and there could also be some zeros, but C0 can be computed by subtracting the positive elements, which is C1 plus C2 plus C3, from the total elements of the array, and this can be computed on the fly. Hence the main idea was not to store the state but store it as counts of values in the array. And let me also explain the transitions. Suppose we were at a state A where it is C1, C2, C3 or C0. Let me also take C0 just for explanation. One of the choice or one of the way in which the indices might occur is we end up at an index, the dice rolls up where the array value is 1. The next one is that we end up at an index where array value is 2. Next, we may end up at an index where array value is 3. Or we might end up at an index where the array value is 0. These are only 4 choices that are possible whenever we roll a dice, right? Now let's try to figure out independently how the state of the array changes for each of these choices. So suppose whenever id is value at that particular index is 1, then the state of array becomes 0. Count of 0 remains same, count of 3 remains same, count of 2 remains same, because whenever 1 is subtracted by 1, it becomes 0. In that case, C0 will be incremented by 1. So the count of 1 will decrease, count of 2 and 3 will remain same, and count of 0 will be incremented by 1 because we subtracted 1 from a position where the value was 1. The second possible choice is when the value is 2. In that case, whenever we are subtracting 1 from a value where it is 2, it decrements the count of 2 by 1 but increments the count of 1 in the entire array. So this will end up with C1 plus 1 and C2 minus 1, and the remaining one remain same. Similarly, whenever we subtract 1 from a position where 3 is present, this will result in extra value with value 2 and reduced value for value 3, a reduced count for value 3. And the fourth choice is that we arrive at a index where value is already 0. In that case, we don't need to perform any operation, so the array state will remain same. So these are the 4 possible choices. We have listed down all of them, and for each of them we need to find out what will be the recurrence relation from transitioning from one state to the other, right? So let's try to figure out the recurrence relation for expected value. Now, as I mentioned, C0 can be computed on the fly, so I am not going to consider this as a state of recursion. So let's say E of C1, C2 and C3 is the expected value of number of operations until the experiment terminates, which is what is asked in the question. Now, let's try to figure out what would be the expected value for C1, C2 and C3. For the first choice, we will have probability P1 of not choosing but arriving at a location where value is 1. So let's assume the probability for that case is P1, and in that case we will end up with this state as we saw in the explanation before. The probability for value arriving at a value 2 would be P2, and performing this operation we would end up in this state. Similar for P3, we will arrive at C1, C2 plus 1, C3 minus 1, and let's say P0 is the probability that we arrive at a location where the value is already 0. Suppose the array was 1, 1, 1, 0, 0, 3, 3. So if we arrive at a location where value is 2, 0, the probability of this event happening is 2 by 7, and with this probability we will end up with the exact same state of the array. So this is the recurrence for expected value. Now let's try to simplify this. Assume this is the final answer that we are computing. Notice that this term is same as this. Let me also write down what will be the values for P1, P2 and P3. So P1 is the probability that we end up at a location where the value is 1, and we know that we have C1 positions where the value is 1 and total number of positions is n. P2 would be, we know that we have C2 count of 2's in the array, so C2 possible choices. Similar for P3, and P0 would be derived from this C1 plus C2 plus C3 whole divided by n. I am assuming this, keeping these variables intact. so that the equation remains simple. Now notice that these two terms are the same, so this is answer. Now simplifying this, we end up by taking this to the left hand side, answer times 1 minus p0, taking the terms to the left hand side. Let's also say that this is E1, E2 and E3 for simplified formula. This will be P1 E1 plus P2 E2 plus P3 E3, and the final answer for this will be P1 E1 P2 E2 plus P3 E3 whole divided by 1 minus P0, and the values for P1, P2, P3 are as what we saw here. So this is the main recurrence or expected value. This is the same as even C1, C2, C3. So notice that we transformed our expected value for the array A1, A2, A3 into the same problem by just storing these counts. Since the array values were only from 1 to 3, that is why we used that. And this is also helpful to store these variables as a state of recursion. So any ci belongs to range 0 to n, hence we can store this, and n is up to 300, hence it is easier to store this values as the state of the recurrence function and compute the probabilities accordingly. Okay, so that is it about the expected value derivation. Let's try to implement this in C++. Okay, first of all, we are going to input n, and this is the counts C1, C2 and C3. As we saw in the explanation, we take an input, the value that is present on the ith dish, increment its count in this variable C1, C2, C3, and start off by finding out the expected value for C1, C2 and C3 in the same manner. This is for printing the answer with 10 decimal points here after the decimal. Okay, so whatever be the answer, this is the precision limit for the question. So let's try to figure out C1, C2 and C3 how they are computed and transitioned. So the base case is that we arrive at a state where all the array elements are 0, which means C1, C2 and C3 are all 0. In that case, the number of operations would be 0, right? No amount of operations will be performed after that. Hence, this is the base case and we handle accordingly. This is for memoization purpose. We will check whether this state is already visited. If it is visited, we will return the answer from there, which is memoized. Else, we will visit this state and update the answer for the particular state of TP. Now, we will need to find out this term, which is the numerator first. So let's try to figure out how it is calculated. The first choice was that we end up at a value where it is 1, and we saw that the probability for that was C1 by n. This is what this term denotes, and the expected value for the next state would be multiplied for that, and this is added to the answer of this numerator part. Next, we will do the same thing for C2 and C3. This term denotes the probability for C2, which is C2 by n, and the expected value for with corresponding states and so on for probability for the third choice. and after that we will need to find out the probability for p0, which is the denominator. So this is what we will arrive at. This will be n minus c1 minus c2 minus c3 whole divided by n, as you saw in the formula, and we will divide the answer by this amount, and this will be computed recursively, and we will going to memorize the answers from top down manner and return the answer from this function. The time complexity for this is the number of unique values the state can take, n values and order n values for each of these three variables, and there are only three transitions, which is constant time, hence the total time complexity will be order n cube. And the space would also be same. Yep, that's it about this. And notice that the answer is initialized with 1, and after that we are adding these terms. So this one denotes that there is one operation that will be performed. That operation is one of these choices, right? And we need to consider that as well, because essentially we are saying that this is the expected value of number of operations. Hence, performing the transitions from any state S to S dash is one operation. Similar on this would be one operation, and we are considering the probabilities of these transitions and trying to find the expected value for these terms, which is the number of operations that will be performed until we reach at a terminating state. That's it about this video. If you found this helpful, do like and comment about it, and if you have any doubts or suggestions, do let me know in the comment section. Thank you.